So welcome to last lecture of this week 1. So now that we have learned spin precession, precessional motion, and how longitudinal magnetization of the sample builds up over time, let us now look at more deeply into magnetic moment. So continuing our discussion on magnetic moment. Okay. So we know that as we have learned already that a particle which has non-zero spin angular momentum also has magnetic moment. In other words, we know now that mu, which is the magnetic moment, is proportional to or is equal to gamma, which is gyromagnetic ratio, is into I, that is the spin angular momentum. Right now, the magnitude of magnetic moment will define actually magnitude and orientation. So magnitude and orientation of mu will decide or decides will decide how strongly it interacts with the applied magnetic field, right? How strongly it interacts with B0, that is applied magnetic field. So this is because your E0 or E is equal to negative mu B naught or B. So here it is a dot product which tells you that it's the orientation which also matters when this interaction is taking place, and then the magnitude of course will matter. That will define if the constant magnetic field is there, the magnitude of the magnetic moment will define how whether the energy of the interaction is weak or high, right? So now the magnitude of mu will be defined by gyromagnetic ratio, right? So here we can see that the magnitude of mu depends on gyromagnetic ratio and spin angular momentum, right? So now gyromagnetic ratio, it's an intrinsic property of a nucleus. So for example, let us look at a few of the spin half nuclei. So spin half nuclei, let us take some examples. So for proton, the gyromagnetic ratio, let us call it as gamma h, is equal to 26.7522 10 to the power 7, and the units are radians per Tesla. Sorry about those explosions. So I actually live next to a testing center where there is a lot of testing going on as of now, so you'll hear some bullets being fired or some bombs being exploded. So that is the in-between sound. Okay. All right. So gamma h is 26.7522 10 to the power 7 radian per Tesla per second, right? Now similarly, let's see the gamma of carbon. It's 6.7283 into 10 to the power 7, same units. Gamma of nitrogen, it is negative 2.7126. Why we are writing these values, so I will just tell you in a minute. Same units. Now gamma of phosphorus is 10.8394 10 to the power 7, and similarly gamma of fluorine 19F is 25.1815 into 10 to the power 7. Now depending on let's say all of them are spin half nuclei, so this is all 13C, 15N, 31P and 19F. So all of them are spin half nuclei. That means their I values are same, but their gamma values are different. So gamma is highest for proton, so you can see that 26.7, and in among these lowest for nitrogen. So that means the magnitude of the magnetic moment would also be in the similar ratio, right? So for example, if I calculate gamma C by gamma H, this will come out to be roughly 1:4. Okay, so you can calculate that. It's a simple calculation. So 6 by 26, this number. So it will roughly be 1 by 4. That means the energy of interaction of this particular nuclei, carbon, as compared to proton, with the same strength of external magnetic field would be 1/4. Okay, so you can also calculate the similar ratios for what will be the ratio for gamma nitrogen to gamma proton. So with respect to proton, what will be the strength of magnetic moment for nitrogen? That will come out to be roughly 1 by 10. Right, so this will be 1 by 10. You can calculate the precise numbers. For fluorine, it will be roughly 94%. Similarly, for phosphorus, it will be roughly 41%. And these numbers will define how strong they are in terms of their magnetic energy of interaction with external magnetic field relative to proton. Okay, so proton, assuming it's the highest gyromagnetic ratio. Actually, if you look at it, the highest is not actually proton, it's the other isotope of proton, which is tritium or tritium, which is basically the 3H, but this is a radioactive isotope, and it is not feasible to carry out any kind of NMR experiments with 3H. You will have to go to sun to borrow some of this 3H, or one of those Spider-Man movies also will have 3H. So this is not possible. So next best is proton. So where proton has second highest gyromagnetic ratio. So we can work with this molecule easily, right? So higher the gyromagnetic ratio, higher will be the magnetic moment, and higher will be the interaction energy. So why we care about the interaction energy? So let us see that in a minute. So we have learnt that any particle, this is again the nuclear Zeeman level discussion. So any particle with spin quantum number I, so let us say spin quantum number I, will have two I plus 1 states, or we can say substates, where each state is defined by Mi values that varies from, this we have already seen, right, -I to +I, and all the integral steps in between, right, with integral increments. That is, so you start with -I, next value of Mi will be -I plus 1, then minus, sorry, not plus, this will be minus I plus 2, and this keeps on going up to +I. So these number of values will be 2I plus 1. So if let us say that if we are talking about I is equal to half, that is spin half particle, that means there will be two states. So if I calculate 2I plus 1, number of states, this will be equal to 1 plus 1, that is 2. Now for each mi is equal to minus half and plus half. These will be the two states characterized by mi values. So a spin half particle will have these two states, and each of these two states will have identical energy in absence of magnetic field. Okay, so the two states are degenerate, no magnetic field. However, when you apply B0, the states will split. One of the states will decrease in energy, and other state will increase in energy, and the degeneracy will be broken, right, the moment you apply B0. But we don't know yet which one is what, whether mi equal to minus half will be the lower state or mi equal to plus half will be the lower state. That we don't know yet, right? So how do we know that? So let us calculate energy of each state here. So we know that classically the interaction energy is given by minus mu dot b, right? This we have already seen. Now quantum mechanical treatment, which again we will see later on. So I'm not covering the quantum mechanical treatment here, but I'm just giving you the result directly. So quantum mechanical treatment tells that energy of a state is equal to negative of mi, that's mi value, gamma b naught h cross, and the units will be in joules. Okay, so this will be the energy of the state. So now let us calculate energy of these two states. So for ease of writing, so let us call this state as alpha state and this state as beta state. So you can just give some names to it. So E for alpha state will be equal to minus of mi is plus half, so half gamma, let us say if we are talking about proton, so 1h nuclei, let's write more legibly. Okay, gamma h b naught h cross, and E of beta will be minus of minus half gamma h b naught h cross. Okay, so this would mean that E alpha is equal to half gamma h b naught h cross, and E beta will be, this will be minus and this will be plus half, because there were two negatives here, gamma h b naught h cross. Now if you calculate the energy difference, so if you see that this is the negative value for all other values are same here, rest of them are all constants, so that means this one will be the low energy state. So that means the alpha state is the low energy state with spin value half, and the beta state will be the high energy state with spin value negative half. But this is true only for gamma greater than 0, that is the positive gamma nuclei, right? So if you take negative gamma nuclei, for example in 15, this alpha beta is reversed. Okay, and this is high energy. All right, now if you take delta E, how much energy is required to carry out the transition, This can be calculated by taking the difference E alpha minus E beta. This will be equal to minus half gamma B0 H cross minus half gamma B0 H cross, which is nothing but gamma B0 H cross. Now this is in joules, right? And you can say this is in, if you want to convert it into hertz or radian per second, so you can remove H cross and then you can call these units in radian per second. And then also you can say that this is nothing but, so there is a negative sign, this is nothing but omega naught, right? So omega naught, which is which we have learnt that this is Larmor precession. So that means the precessional frequency of the spins in presence of magnetic field will be equal to the Zeeman splitting energy difference. So if you talk in terms of frequency units, then this frequency will be same as the precessional frequency. Okay, this has a lot of importance when we are doing when we later on learn the resonance phenomena. So this difference is nothing but the Larmor precession. Okay. Right. Okay. So for let us calculate this value for protons. So for proton nuclei, 1H nuclei, gamma H is equal to, we know the value 26.7. This is a constant, 10 to the power 8 radians per Tesla per second, and let us say that the B0 is 11.74 Tesla magnetic field strength. Okay, now at these values, if you calculate omega 0, so you can easily calculate, just take the product, and omega 0 comes out to be 499.859 into 10 to the power 6 hertz, or you can approximately call it as 500 megahertz. So when you typically go in any NMR lab, so you will be seeing that you will be talking that, okay, I want to record my spectrum at 400 megahertz machine, or 600 megahertz machine, or 900 megahertz machine, and so on. So this is a standard norm to talk the strength of the field in terms of the precessional frequency or the Larmor precession frequency of the proton nuclei for that field. So we can also call 500 magnet as 11 Tesla magnet, or 600 magnet as 14 Tesla magnet, and 400 magnet as 9 Tesla magnet, and so on and so forth. But this is in some of the labs, this is also a norm that you call it as 400 magnet, 500 magnet, or 600 magnet, and so on and so forth. Okay, so so you can precisely calculate the Larmor precession once you know the gamma value and the B0 value. So a little home exercise for you. So please try to do it so that you are aware of this calculation. I mean, not that it's a very difficult one, so it's a very simple calculation, but just so that you're aware of what are the units and what kind of numbers you're handling later on, right? So what is the Larmor precessional L capital actually? Frequency of 1H and 13C in Earth's magnetic field. So you can assume Earth's magnetic field to be equal to 50 approximately. So Earth's magnetic field is different at different locations because of obvious reasons. So but Earth's magnetic field you can assume in general as 50 micro Tesla. Okay. Alright, so assuming this value, calculate the Larmor precessional frequency of proton and C13 nuclei. So you would get a sense of how fast a proton or a C13 sitting on Earth is precessing by itself, okay, without any additional magnetic field required. So there is some precession, some basal precession is always going on because of Earth's magnetic field. So your exercise is to calculate that precessional frequency. Okay. So now that we know the energy, that there is a ground state energy, there is a excited state energy. So let us the moment you have the energy difference, the moment you say that okay, there is a E alpha state, or there is a alpha state and beta state corresponding to E alpha energy and E beta energy, and then there is a delta E. The moment you have created the Zeeman splitting, you can carry out a transition, and then you can ask different questions by doing this spectroscopy, right? So now let us also calculate what is the corresponding population in alpha state and population in beta state. Okay, so P alpha and P beta. So the population goes by actually very simple law, which you all would know. It's the Boltzmann distribution. So Boltzmann distribution says n alpha, that is the number of particles in alpha state, divided by n beta, that is the number of particles in beta state, where alpha is the ground state and beta is the excited state, is equal to exponential of E beta minus E alpha divided by kBt. Okay. This is the expression. So very simple expression. So all you want to do is, if you want to calculate the ratio of the two populations in alpha and beta states, you have to take the difference in the energy and then divide it by kBt and take the exponential. Okay, so for let us calculate this value for proton at 11.74 Tesla magnetic field at room temperature. So that is 298 Kelvin. Okay, so let us do this simple calculation. So let us first calculate E beta minus E alpha divided by kBt. So this number, so now you know the delta E is equal to gamma B naught by H cross. So I have taken E beta minus E alpha, so there is no negative sign here. If you take E alpha minus beta, there would be a negative sign, right? Divided by kBt. Now this is, it's a long expression, but then these are all constants, so you know the values. 26.7522 10 to the power 8 radians per Tesla per second. B0 is 11.74 Tesla. H cross is 1.05 10 to the power minus 34. The units are joule radian per inverse sorry, not second inverse, this is second, divided by kBt. kB is the Boltzmann constant, which takes the value as 1.38 into 10 to the power minus 23 joules per Kelvin, and temperature is room temperature, so 298 Kelvin. So let us first see if the units are cancelling out, because This is supposed to be a unitless quantity, so Kelvin goes with Kelvin, Joule goes away with Joule, then second inverse goes away with second inverse, Tesla, Tesla, radian inverse radian. Okay, so none of the units are pending. Now this amounts to be, this whole thing comes out to be 0.00008. Okay, so idea is that this number is very smaller, or very small as compared to number 1. Okay, why do I say that? Because we are going to calculate the exponential of this number, right? Okay, so let's calculate. So let me remind you that Ex can be also expanded in terms of Taylor expansion. So this can be written as 1 plus x square plus 2 factorial divided by 2 factorial plus x cube divided by 3 factorial all the way to infinity, right? Now if you remember your class 11th mathematics, so this Taylor series you must have learned in class 11th, right? If x is less than 1, if x is very small, the higher powers of x, like x square, x cube, x4, they all vanish because the number becomes too small or too insignificant to be added to this number. So that means you can approximately say that e power x is equal to 1 plus x for the values of x which are very small, smaller than 1. So for this case 0.00008, this thing holds, and you can call this as 1 plus x. So that means now we can, so let me go to the next page. So that means you can say n alpha divided by n beta is exponential 0.00008, and this can be written as 1 plus 0.00008, that is 1.00008. Now once you know n alpha by n beta, and you know that n alpha plus n beta is 1, you can assume it to be, right, because that will be the total population. So you can calculate n alpha, which will come out to be roughly 50. This is a simple calculation you should be able to do, so I'm not doing it for you. 0.004%, and n beta will be 49. So 100 minus 50.004, 996%. Okay. So that means at 25 degrees Celsius, 11.74 Tesla magnetic field. So remember that it's a very big magnetic field, because Earth's magnetic field, you know how magnetic compass works at Earth's magnetic field at 50 micro Tesla, right? So this is just to give you an idea. So Earth's magnetic field strength is of the order of 50 micro Tesla. Then MRI machines, most MRI machines work at 3 Tesla. The NMR magnets typically go from 9 Tesla to, nowadays maximum strength available is 28 Tesla. Okay, so much stronger than Earth's magnetic field. And this calculation what we have done here is at 11.74 Tesla. Okay, so at 11.74 Tesla and room temperature, the population excess is only 0.008%, right? So that means very small increase in population in alpha state as compared to beta state. So the energy difference is so small that almost both the states are equally populated with very slight excess in alpha state as compared to beta state. Okay, so this tells you that the NMR is highly insensitive technique. Okay, because the population difference is so small that the any transition which is to be observed from alpha state to beta state has to be amplified to a large extent so that you can see it, you can visualize it. Okay, so this is done by the electronics in the instrument, and we are able to see, but having said that, the the technique is very very insensitive, and you need a large amount of sample so that there is appreciable excess concentration in alpha state as compared to beta state. Okay, so now if the if this is the situation for protons, so imagine that the interaction energy is further less for C13. Let's it's almost 1/4. So the population difference would also be smaller for carbon or other insensitive nuclei. So these so proton is the most sensitive of the lot, as I said, next to 3H. So proton is most sensitive, and all other nuclei are hence called as insensitive nuclei. So carbon and nitrogen, fluorine is almost sensitive as proton. Phosphorus, these are all called as insensitive nuclei because their population difference is further reduced because of their less gamma. So gamma is less, therefore the magnetic moment is less. If the magnetic moment is less, the energy difference is going to be less. If energy difference is going to be less, the population difference is going to be less. And if population is going to be less, population difference is going to be less, then the transition efficiency would also be, or you can also say that the signal to noise ratio would also be less, right? So let us now calculate, or let me give you another home exercise. A simple one. So calculate population difference for proton and 13C at 1200 megahertz magnet. So I'm using a different nomenclature for this magnet. I'm not telling you the magnetic field strength, I'm telling you 1200 megahertz magnet. Calculate the population difference for proton and C13 at 298 Kelvin. By the way, so when we say 298 Kelvin, when we use this approximation that X is very very less than 1, so here we meant that the gamma B naught is much less than kBt, right? Because we were calculating this ratio which comes out to be 0.00008 for proton at 298. So that means temperature is very high, which makes this number very small, right? So this is the fact which we are assuming in calculating the population difference, right? So this approximation is termed as, and we will see later on its use in density matrix formalism. Let's not go into those details right now. So this approximation is called as high temperature approximation. So although we are working at room temperature only, but this is already a very high temperature for these spins. So this is called as high temperature approximation. All right, I think with this we finished this week's lecture, and next week we are going to start with Bloch equations. So that's all for today. Thank you.